Section 1. The Origins of String Theory. The story of string theory begins not with grand visions of unifying the cosmos, but in the more grounded world of nuclear physics. In the late 1960s, physicists were attempting to understand the strong nuclear force, the fundamental interaction that holds protons and neutrons together in atomic nuclei. At the time, experimental data from particle accelerators revealed a bewildering zoo of subatomic particles, many of which seemed to fall into patterns suggestive of deeper symmetries. In 1968, Italian physicist Gabriele Veneziano made a curious discovery. While searching for a mathematical function to describe the scattering of strongly interacting particles, he stumbled upon an old formula from the 18th century, the Euler beta function. Remarkably, this function fit experimental data far better than expected. What Veneziano didn't know at the time was that this function was secretly describing the dynamics of a vibrating string. Shortly after, theorists like Yoichiro Nambu, Holger Nielsen, and Leonard Susskind realized that the beta function could be interpreted not just as a useful mathematical tool, but as evidence of a deeper physical picture, that elementary particles might not be point-like dots, as previously assumed, but tiny, one-dimensional strings vibrating at different frequencies. Each unique vibration would correspond to a different particle, much like different notes on a violin string. This was the birth of what would come to be known as string theory. But it was not yet the grand, unifying framework we associate with the term today. Early string theory, called the dual resonance model, was narrowly focused on hadronic physics. It wasn't until researchers discovered that the theory inevitably predicted the existence of a massless spin 2 particle, consistent with the graviton, the hypothetical quantum of gravity, that string theory began to hint at something far more ambitious. And so, from its humble beginnings in nuclear physics, a new theoretical frontier began to open, one that promised to bridge the gap between quantum mechanics and general relativity. But this promise wouldn't be fully recognized for over a decade. Section 2. The Rise and Fall of the First String Theory Era. As the 1970s dawned, excitement began to build around the idea that string theory might not just be a model for nuclear forces, but a potential framework for unifying all fundamental interactions, including gravity. The discovery that string theory naturally contained a graviton, a massless particle with spin 2, was a profound moment. Unlike other quantum field theories, string theory didn't need gravity to be added in. It emerged organically from the mathematics itself. This was revolutionary. Physicists had long struggled to reconcile the smooth geometry of Einstein's general relativity with the probabilistic framework of quantum mechanics. Attempts to quantize gravity using standard particle-based approaches led to infinities and mathematical inconsistencies. But string theory offered a glimmer of hope. The extended nature of strings, unlike point particles, helped smooth out these troublesome infinities. String theory seemed to offer a built-in ultraviolet regulator, a way to avoid the catastrophic breakdowns that plagued quantum gravity. However, there was a problem. Many problems, in fact. First, the early versions of string theory required 26 space-time dimensions in order to be mathematically consistent, far more than the 4, 3 spatial and 1 temporal, that we observe. To make matters more puzzling, the theory predicted the existence of tachyons, hypothetical particles that traveled faster than light and indicated instability in the vacuum. Moreover, experimental evidence didn't seem to support string theory's original goal of describing the strong force. Around the same time, quantum chromodynamics, QCD, was rising to prominence. QCD, a quantum field theory describing interactions between quarks and gluons, quickly became the accepted explanation for the strong nuclear force. In this new light, string theory appeared unnecessary, its role seemingly eclipsed by the success of QCD. As a result, interest in string theory faded. By the late 1970s, many physicists had moved on. String theory was considered a mathematical curiosity at best, a failed attempt at worst. It retreated into the background, maintained by a small but dedicated group of researchers who believed it still held untapped potential. What they didn't yet realize was that a major breakthrough was looming, one that would revive string theory and place it at the center of the quest for a theory of everything. Section 3. Supersymmetry and the Superstring Revolution. The quiet persistence of a handful of theorists paid off in the early 1980s, when a powerful new idea breathed fresh life into the fading string theory framework, supersymmetry. Supersymmetry, often abbreviated as SUSY, is a proposed symmetry of nature that links two fundamentally different types of particles, bosons, which carry forces, and fermions, which make up matter. In a supersymmetric theory, each boson has a fermionic partner, and vice versa. This elegant pairing had intriguing mathematical benefits, including the ability to cancel out troublesome infinities that plagued many quantum theories. When supersymmetry was woven into the fabric of string theory, it led to the birth of a new and improved framework, superstring theory. Unlike its earlier cousin, superstring theory required only 10 space-time dimensions for consistency, a significant improvement over the original 26. Even better, the inclusion of supersymmetry removed tachyons and made the theory much more stable. In 1984, string theory experienced what would later be called the first superstring revolution. This turning point was catalyzed by a landmark paper written by Michael Green and John Schwartz. Their work demonstrated that a particular type of superstring theory could avoid quantum inconsistencies known as anomalies, mathematical breakdowns that would otherwise render a theory invalid. The Green-Schwartz mechanism showed that superstring theory wasn't just beautiful, it was viable. This sparked an explosion of interest. Researchers quickly discovered that superstring theory didn't just include gravity, it also had the potential to unify all four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Even more tantalizing, it naturally incorporated gauge symmetries and chiral fermions, both key features of the standard model of particle physics. By the mid-1980s, 5 consistent versions of superstring theory had been identified, each describing slightly different physical scenarios. Rather than being seen as a flaw, this multiplicity hinted at a deeper, underlying structure. But for now, each theory was studied independently, with the hope that one might ultimately emerge as the correct theory of everything. At long last, string theory was no longer a fringe idea. It had become one of the most exciting and promising fields in theoretical physics. But the best was yet to come, because hidden beneath the surface of these 5 theories was something even more profound, waiting to be uncovered in the next revolution. Section 4. The 5 Superstring Theories. By the late 1980s, string theory was no longer a single unified theory. It was 5. Each version was mathematically consistent, incorporated supersymmetry, and included gravity. But they differed in technical details. The types of strings they allowed, the ways those strings interacted, and the kinds of symmetries embedded in their structure. Let's briefly explore each of the 5. 1. Type 1. This theory includes both open and closed strings. Open strings have 2 endpoints, while closed strings form loops. Type 1 theory is unique in allowing both types and incorporates SO 32 gauge symmetry. It's also non-chiral, meaning it does not distinguish between left-handed and right-handed particles. 2. Type IIA. This theory deals only with closed strings and is non-chiral. It allows for a wide range of Branes, multi-dimensional objects, which would later become central to string theory's evolution. Type IIA is related to higher dimensional physics and hinted at deeper geometric structures. 3. Type IIB. Also a closed string theory, type IIB is chiral, making it more compatible with the structure of the standard model. It includes both strings and various types of Branes and possesses a rich symmetry structure that would become important in later dualities. 4. Heterotic So, 32. This version is something of a hybrid. It combines left moving modes from a bosonic string in 26 dimensions with right moving modes from a superstring in 10 dimensions. The result is a closed string theory with So, 32, gauge symmetry, promising for unifying particle physics with gravity. 5. Heterotic E8 times E8. Similar to its So, 32, cousin, this theory also uses asymmetric construction, but with a different gauge symmetry. E8 times E8, a mathematically rich and highly symmetric group. This version became particularly popular among physicists exploring string theory's connection to the real world, as its symmetry group seemed well suited for building realistic particle physics models. At first glance, the existence of 5 separate theories of everything was unsettling. Physics thrives on unification, and having multiple contenders for a final theory was more confusing than enlightening. Were these 5 rivals? Or could they be different expressions of the same, deeper truth? Physicists began to notice peculiar hints, mathematical coincidences and symmetries that suggested the 5 theories were not as separate as they appeared. These clues would eventually lead to a second revolution, one that would reshape the entire landscape of theoretical physics and reveal a hidden unity beneath the surface. Section 5. Dualities and the Hidden Unity. By the early 1990s, the theoretical physics community was buzzing with possibility and a growing suspicion. Despite their surface-level differences, the 5 superstring theories shared deep structural similarities. Could they all be connected? The answer came in the form of dualities, mathematical symmetries that showed how seemingly distinct string theories could, under the right conditions, be equivalent. These weren't just coincidences or clever tricks. They were profound revelations that certain theories, when viewed from a different angle, were simply repackaged versions of one another. 2 main types of dualities drove this transformation. 1. T-duality. This duality links theories compactified on different-sized circular dimensions. It shows that a string theory compactified on a circle of radius r is physically equivalent to one compactified on a circle of radius 1/r. This counterintuitive result highlights the unique nature of strings. Unlike point particles, strings can wrap around dimensions. As a result, shrinking a dimension doesn't lead to disappearance, it leads to new physics. 2. S-duality. This duality relates theories at strong coupling, where interactions are intense, to those at weak coupling, where interactions are gentle. In essence, it provides a powerful mathematical lens. A theory that's impossible to solve directly due to strong interactions can be translated into a more manageable weakly coupled dual version. S-duality revealed that certain string theories were just strong coupling mirrors of one another. With these dualities, physicists began to map out the deep connections between the 5 string theories. What emerged was not 5 separate frameworks, but 5 windows into a single underlying theory. This realization culminated in the second superstring revolution, led by theorists like Edward Witten. In 1995, Witten proposed that all 5 string theories were special cases or limits of a more fundamental 11-dimensional theory, which he dubbed M-theory. Though the exact nature of M-theory remained mysterious, the conceptual breakthrough was enormous. Strings, it turned out, were just one aspect of a much richer framework involving membranes, branes of higher dimensions, and a deeper geometric unity. String theory was no longer a collection of rival models. It was a network, connected by dualities, forming a single, coherent landscape. This was a major conceptual leap. It meant that the fundamental laws of physics might not be tied to a particular mathematical formulation, but could instead emerge from a web of interconnected perspectives. With the rise of M-theory, string theory matured into something far more ambitious. But to explore its full implications, physicists had to delve into the geometry of higher dimensions, the mysterious role of branes, and the strange shape of the compact spaces hidden from view. Section 6. The geometry of extra dimensions. One of the most striking features of string theory, and a major departure from everyday intuition, is its insistence on extra spatial dimensions. To be mathematically consistent, superstring theory requires 10 dimensions, 9 spatial and 1 time, while M-theory extends that to 11. Since we only experience 3 dimensions of space and 1 of time in our everyday lives, the natural question arises: where are the other dimensions hiding? The answer lies in a process called compactification. In string theory, the additional dimensions are thought to be curled up into tiny, intricate shapes at every point in space, so small that they evade direct detection. These compact dimensions don't simply vanish. Instead, they form geometric manifolds that influence the behavior of strings and particles. The most well-studied of these manifolds are known as Calabi-Yau spaces. A Calabi-Yau manifold is a special type of 6-dimensional shape that preserves a certain amount of supersymmetry and satisfies complex mathematical conditions involving curvature and topology. What makes these spaces so fascinating is that their shape directly determines the properties of the universe. The way strings vibrate within a given Calabi-Yau manifold defines what particles exist, their masses, forces, and even the structure of physical laws. In this sense, the geometry of the compactified dimensions acts like a cosmic blueprint. Different Calabi-Yau shapes lead to different low-energy physics, meaning, potentially, different universes with different fundamental constants. This realization has vast implications, not just for string theory but for cosmology and our understanding of why our universe is the way it is. However, compactification comes with immense challenges. The number of possible Calabi-Yau shapes is enormous, perhaps on the order of 10 to the power of 500 or more. This leads to what's known as the string landscape problem. There may be an unimaginably vast number of mathematically consistent ways to compactify string theory, each yielding a different version of physical reality. This raises profound philosophical and scientific questions. Are we living in a universe that was somehow selected from this vast landscape? Or is our universe just one among many, an accidental result in a multiverse of possibilities? These ideas remain hotly debated, but they show just how deeply geometry and physics intertwine in string theory. In this realm, space is not a passive stage where physics plays out. It is a dynamic, encoded participant in the laws of nature. Section 7. Branes, Membranes, and the Extended Objects of M-Theory. As physicists explored the unifying power of M-Theory, they realized that strings were just the beginning. Embedded within this higher-dimensional framework were even more exotic objects, higher-dimensional analogs of strings, collectively known as branes. The term brane is short for membrane, and in M-theory, branes come in a variety of dimensions. A 0 brane is a point-like particle. A 1 brane is a string. A 2 brane is a 2-dimensional membrane. This continues up to higher-dimensional objects like 5 branes and beyond. These objects can stretch across the extended dimensions of spacetime, and some are even thought to be infinite in size. Among the most studied are D-branes, short for Dirichlet branes. These are surfaces on which open strings can end, and they play a crucial role in string dynamics. For example, the ends of an open string might be anchored to a D-brane, meaning the brane acts like a physical boundary for the string's motion. In this picture, the vibrations of strings attached to branes give rise to the familiar particles of the standard model. But branes are more than just scaffolding for strings. They are dynamic, physical entities in their own right. They can carry energy, warp spacetime, and interact with other branes and strings. Some theories even propose that our entire universe might be a 3-brane, essentially a 3-dimensional membrane, floating within a higher dimensional space. In this view, all the particles and forces we observe are confined to the brane, while gravity can leak into the extra dimensions. This idea has sparked novel theories of brane-world cosmology, where the early universe may have resulted from the collision or interaction of branes. These interactions could even leave detectable traces in the cosmic microwave background or gravitational waves. M-theory itself is thought to include not just strings, but 2 branes and 5 branes as fundamental building blocks. This expanded ontology has opened new mathematical avenues and deepened our understanding of what matter and space might truly be made of. In this brane-rich landscape, the classical notion of particles as points gives way to a universe constructed from vibrating, fluctuating, and stretching geometric entities, a picture far more complex, but also far more unified than anything offered before. Section 8. Black holes, information, and the power of string theory. One of the most unexpected triumphs of string theory came from its ability to illuminate the deep mysteries of black holes, those enigmatic regions of spacetime where gravity becomes so intense that not even light can escape. For decades, black holes posed a profound problem for theoretical physics. According to classical general relativity, a black hole is defined by just a few properties: mass, charge, and spin. But quantum mechanics insists that physical systems must retain information. This led to the black hole information paradox. If black holes eventually evaporate via Hawking radiation, as Stephen Hawking showed in the 1970s, then where does the information go? Does it vanish forever, violating quantum law? Or is it somehow preserved? String theory offered a breakthrough. In 1996, Andrew Strominger and Kamran Vafa showed that certain types of black holes, especially extremal ones with highly symmetric conditions, could be modeled in string theory as bound states of d-branes. These branes, with strings attached, created a microscopic accounting of the black hole's entropy, a measure of its internal degrees of freedom. Their calculation matched precisely the famous Bekenstein-Hawking entropy formula, which relates the entropy of a black hole to the area of its event horizon. For the first time, physicists had a concrete statistical explanation for black hole entropy, what the microscopic constituents actually were. This was a stunning success for string theory and provided strong evidence that it could serve as a viable quantum theory of gravity. But the implications went even deeper. Subsequent developments, particularly in the context of the AD/CFT correspondence, which we'll explore in the next section, suggested that black holes do not destroy information. Instead, the information is encoded in the quantum states of the radiation, even if we don't yet fully understand the mechanism. In this view, string theory doesn't just patch the holes in our understanding of black holes. It offers a new framework in which gravity, quantum mechanics, and thermodynamics are unified. It transforms black holes from mysterious endpoints into laboratories for testing the quantum structure of spacetime. These insights have sparked ongoing debates and new theories, such as the firewall controversy, the ER equals EPR conjecture, and the role of entanglement in the fabric of spacetime. Through it all, string theory remains a central tool, often the only tool, capable of bridging these deep conceptual divides. Section 9. The AD/CFT correspondence and holographic duality. In 1997, string theory took another astonishing leap forward with a bold proposal by Argentine physicist Juan Meldacena. His idea, now known as the AD/CFT correspondence, revealed a deep and unexpected connection between gravity and quantum field theory, one that would reshape our understanding of space, time, and information. At its core, the AD/CFT correspondence is a type of holographic duality. It posits that a theory of gravity in a curved spacetime called anti-de Sitter space, ADS, is equivalent to a conformal field theory, CFT, defined on the lower dimensional boundary of that space. In simpler terms, It suggests that a gravitational universe in a higher number of dimensions can be completely described by a quantum theory without gravity in fewer dimensions. This was revolutionary. For example, in the most well-studied case, string theory in a 5-dimensional add space is equivalent to a 4-dimensional n equals 4 supersymmetric Yang-Mills theory, a quantum field theory similar to those used to describe particle interactions. Every object, event, and gravitational phenomenon inside the add space has a dual representation in the boundary theory. This duality accomplishes something profound. It allows physicists to study quantum gravity, a notoriously difficult subject, using the well-understood tools of quantum field theory. It also provides a concrete realization of the holographic principle, the idea that the information content of a volume of space can be encoded on its boundary, much like a hologram stores a 3D image in a 2D surface. The implications of add/CFT are far-reaching. 1. It offers insight into the information paradox of black holes, suggesting that information may be preserved holographically. 2. It provides a powerful framework for studying strongly coupled quantum systems, such as those found in nuclear and condensed matter physics. 3. It hints that spacetime itself may emerge from more fundamental quantum entanglements, an idea at the frontier of quantum gravity research. While our universe does not appear to be described by anti-de Sitter space, our spacetime is closer to de Sitter space due to its accelerating expansion. The correspondence remains a mathematical laboratory for testing ideas about quantum gravity, information, and the emergence of geometry. The add/CFT correspondence has become one of the cornerstones of modern theoretical physics. More than a tool, it is a glimpse into the possibility that the fabric of the universe is fundamentally quantum and holographic, a perspective that may ultimately transform how we understand everything from black holes to the Big Bang. Section 10. The String Landscape and the Multiverse Debate. As string theory evolved, it revealed a truth both awe-inspiring and unsettling. The theory does not lead to a single unique solution for the structure of the universe. Instead, it allows for an enormous number of possible configurations, each one a different way of compactifying the extra dimensions, choosing geometric shapes, Brane arrangements, and field values. This realization gave rise to what is now known as the string landscape. The term refers to the vast space of possible vacuum states, each corresponding to a different universe with its own set of physical laws, particle types, force strengths, and even numbers of dimensions. Estimates of the number of viable solutions vary, but the commonly cited figure is staggering: 10 to the power of 500 or more. That's not just a variety of particles, it's a near-infinite array of possible realities. This led to one of the most profound and controversial ideas in theoretical physics: the multiverse. In the multiverse picture, our universe is just one bubble in an unimaginably large cosmic foam, each bubble representing a different region of the string landscape with its own unique physics. The mechanism often invoked is eternal inflation, a process by which the universe continuously spawns new regions, each falling into different vacuum states of string theory. In this framework, many of the physical constants we observe, such as the cosmological constant or the mass of the electron, are not uniquely determined by deep physical laws. Instead, they are environmental values, set by the conditions in our specific region of the multiverse. We observe these constants because we exist in a region where they permit the formation of complex structures like galaxies, planets, and life, a concept known as the anthropic principle. This interpretation has sparked fierce debate. On one hand, it offers an elegant way to explain why the laws of physics appear so finely tuned for life. On the other, it challenges the traditional scientific ideal of predictive power. If anything that can happen does happen somewhere in the multiverse, then how do we test the theory? What counts as a falsifiable prediction? Critics argue that the multiverse risks pushing string theory beyond the bounds of empirical science. Supporters counter that the landscape is a natural consequence of the theory's mathematical structure, and that ignoring it would be intellectually dishonest. Regardless of where one stands, the landscape and multiverse debate has changed the conversation. It has reframed fundamental physics as not just a search for unique laws, but a quest to understand why this universe, among so many possibilities, is the one we inhabit. Section 11. String Cosmology and the Early Universe. Cosmology, the study of the origin, structure, and evolution of the universe, has long been the domain of general relativity and the Big Bang model. But string theory brings a powerful new perspective to the table, one that aims to extend our understanding beyond the singularity at the beginning of time. In the standard cosmological model, the universe began as a point of infinite density and temperature, known as the Big Bang singularity. But singularities signal a breakdown of known physics. String theory, with its extended objects and smoothed interactions, offers a potential way to resolve these infinities and describe the very earliest moments of the universe in a coherent quantum framework. One promising avenue of research is string cosmology, which applies the principles of string theory to early universe scenarios. In this context, the universe's evolution may have been influenced not only by quantum fields, but also by the dynamics of strings and branes. For instance, in brane inflation models, the early universe is envisioned as a higher-dimensional space in which our 3D universe is a brane moving through a larger dimensional bulk. The energy driving inflation, the rapid exponential expansion of space, is supplied by the motion or interaction of branes. When two branes collide or interact, they release vast amounts of energy, which can give rise to the hot, dense conditions associated with the traditional Big Bang. Another bold idea is the ekpyrotic scenario, in which the universe's birth is not from a singularity, but from the slow approach and eventual collision of branes. Instead of expanding from a point, the universe arises from a pre-existing state, avoiding the classical Big Bang entirely. This model offers alternative explanations for the observed homogeneity of the cosmos and the origin of structure, while potentially avoiding the problems of singularities. String cosmology also has implications for the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Certain features in the CMB, such as non-Gaussian patterns or subtle anomalies, might offer hints of stringy physics imprinted on the early universe. These are areas of active research, where theory and observation are beginning to intersect. Crucially, string theory doesn't just seek to describe what happened after the Big Bang. It aims to describe the conditions before and beyond it. In doing so, it reimagines the origin of time, space, and energy, replacing singularities with a more graceful, quantum-informed genesis. While many of these models remain speculative, they push the boundaries of cosmology into realms that traditional physics struggles to reach, offering new paths to understanding the deepest origins of the universe. Section 12. Experimental Challenges and the Quest for Evidence. String theory, with all its mathematical elegance and sweeping unifying power, stands as one of the most ambitious frameworks in the history of physics. But for all its theoretical beauty, it faces a serious challenge: a lack of direct experimental evidence. Unlike theories such as general relativity or quantum electrodynamics, which have been confirmed to extraordinary precision through experiment, string theory operates at energy scales far beyond the reach of current technology. The characteristic length scale of a string is on the order of the Planck length, about 10 superscript 3 meters, far smaller than anything we can probe with today's particle accelerators. The energy required to excite a string into its higher vibrational modes, the key to revealing its stringy nature, would be around the Planck energy, approximately 10 superscript 1 GeV. For comparison, the Large Hadron Collider, LHC, the most powerful particle accelerator on Earth, reaches energies around 10 GeV, 15 orders of magnitude too low. This leaves string theorists with a difficult task: how to connect their models to observable phenomena. Several avenues of indirect evidence are actively being explored. 1. Supersymmetry. Many string theory models predict that supersymmetry should exist at low energies. If supersymmetric partner particles were discovered in high-energy experiments, it would be a major boost for string theory. However, as of now, no SUSY particles have been detected. 2. Extra dimensions. If extra spatial dimensions exist, they might be revealed through subtle gravitational effects or missing energy signatures in particle collisions. The LHC has searched for such signs, but so far, no deviations from the standard model have been observed. 3. Cosmological imprints. The early universe offers a unique testing ground. Models of brane inflation or stringy corrections to inflation could leave faint imprints in the cosmic microwave background or in primordial gravitational waves. Observatories like the Planck satellite and future missions like LISA aim to detect such signals. 4. Black hole physics. String theory has made testable predictions in highly symmetric cases, such as the microscopic origin of black hole entropy. While these tests are theoretical in nature, they lend credibility to the idea that string theory captures important aspects of quantum gravity. 5. Mathematical predictivity. In many ways, string theory has become a tool for exploring new mathematics. The consistency of the theory has led to deep mathematical discoveries, many of which later found applications in seemingly unrelated areas of physics. This surprising effectiveness hints that the theory may be tapping into something fundamentally true about the universe. Still, the lack of clear experimental evidence remains the theory's greatest vulnerability, and the source of ongoing debate. Critics argue that without falsifiable predictions, string theory veers too close to metaphysics. Proponents counter that it's premature to judge a theory of such immense scope before the necessary tools exist to test it. History has shown that experimental lag is not uncommon in physics. It took decades for Einstein's predictions about gravitational waves to be confirmed. If string theory is correct, its testability may simply lie beyond the current technological horizon, waiting for the next generation of instruments, or perhaps a breakthrough that reframes the way we probe reality. Section 13. Mathematical rigor and unexpected connections. While string theory's experimental verification remains elusive, it has flourished in another domain: pure mathematics. In fact, many physicists and mathematicians now see string theory not only as a framework for unifying physics, but also as a discovery engine for new and surprising mathematics. This relationship between physics and mathematics is nothing new. Historically, theoretical physics has often driven mathematical innovation. Newton's calculus, Einstein's tensors, or Dirac's spinors are classic examples. But string theory takes this synergy to an entirely new level. In trying to make sense of the theory's compact dimensions, branes, and dualities, physicists stumbled upon deep structures in geometry, topology, and algebra that mathematicians had never seen, or had seen, but not understood in the same light. One of the most famous examples of this is mirror symmetry. Mirror symmetry, first noticed in string compactifications, suggests that certain Calabi, Yau manifolds, complex six-dimensional shapes used in compactifying extra dimensions, come in pairs. These mirror manifolds, though geometrically distinct, yield equivalent physical predictions. When one side is difficult to compute, the mirror side may be simple. This unexpected duality provided tools for solving long-standing mathematical problems in enumerative geometry, problems that had nothing to do with strings at first glance. This wasn't an isolated incident. String theory has led to 1. New insights in knot theory through its connections to topological quantum field theory. 2. Advances in moduli space geometry, the mathematical description of all possible shapes of extra-dimensional spaces. 3. Development of powerful algebraic tools like vertex operator algebras, crucial in describing string interactions. 4. Contributions to number theory, through links with modular forms and string partition functions. What's remarkable is that string theory, originally built as a tool to describe physical phenomena, has become a predictive framework for mathematics itself. In some cases, the mathematics was only later rigorously proven by mathematicians, years after string theorists had used it based on physical intuition. This cross-pollination between fields has not only elevated string theory's status in the mathematical community, but also suggested that the boundaries between physics and mathematics may be more artificial than real. Some even argue that string theory represents a glimpse into the deeper language of nature, a kind of pre-geometry from which both math and physical laws emerge. It's a strange inverted scenario. A physical theory criticized for its lack of empirical testability is, at the same time, delivering rigorous and groundbreaking mathematics. Whether or not string theory turns out to be the final theory of nature, its mathematical legacy is already undeniable. Section 14. The Future of String Theory. As we stand today, string theory occupies a unique place in the scientific landscape. It is both a revered mathematical framework and a theoretical frontier, full of promise and open questions. But where does it go from here? What does the future hold for this ambitious attempt at a theory of everything? One direction lies in deepening our understanding of M-theory. While M-theory is widely regarded as the overarching structure unifying all 5 superstring theories, its full formulation remains elusive. Much of what we know about it comes from approximations, dualities, and special cases. A complete, non-perturbative description of M-theory, one that doesn't rely on expansions or limits, remains a major goal. Some physicists believe it may require a radically new conceptual framework, possibly involving emergent spacetime or pre-geometric quantum systems. Another frontier involves the quantum structure of spacetime. String theory has already shown that gravity and quantum mechanics can coexist in a consistent framework. But more work is needed to explain how classical spacetime itself arises from quantum entanglements and stringy structures. Approaches like the ER equals EPR conjecture, holographic entanglement entropy, and tensor networks hint at a future where space and time are not fundamental, but emergent properties of deeper quantum information dynamics. String theory may also play a crucial role in understanding de Sitter space, which more accurately models our accelerating universe. Most string theory work has focused on anti-de Sitter spaces, which are mathematically convenient but don't reflect our observed cosmology. Constructing stable, realistic de Sitter vacua in string theory is a major challenge, and one that could bridge the gap between theory and observation. In parallel, there's growing interest in the interface between string theory and data science. With the discovery of the vast string landscape, perhaps 10 to the power of 500 possible vacua, physicists are increasingly turning to machine learning, AI algorithms, and statistical methods to explore this complex terrain. These tools may help identify patterns or universes that exhibit desirable physical properties, offering new insights into the structure of the landscape. Meanwhile, the dialogue with mathematics continues to flourish. String theory may drive the discovery of entirely new mathematical realms, just as it did with mirror symmetry. As this feedback loop between physics and math deepens, it's likely to reshape both fields, blurring their boundaries and forging unexpected connections. Ultimately, the future of string theory may depend not only on technology or theoretical breakthroughs, but on how we define progress in physics. Is it enough to build a self-consistent, unifying framework? Or must that framework also yield predictions we can test with today's instruments? As research continues, string theory is evolving, not as a closed system of ideas, but as a living framework that adapts, expands, and surprises. Whether it becomes the final theory of nature or merely one chapter in a larger story, its influence on science is already profound. Section 15. String Theory in the Bigger Picture. As we close this journey through the rich, intricate world of string theory, it's worth stepping back and asking, what does it all mean? What role does string theory play in the larger quest to understand the universe? String theory began as an attempt to explain the behavior of subatomic particles, but it evolved into something far greater. A candidate for a unified theory of everything, combining gravity, quantum mechanics, and the fundamental forces into a single mathematical framework. Along the way, it transformed our view of reality. From particles to strings, from 3 dimensions to 10 or 11, from fixed spacetime to dynamic, emergent geometry. Yet string theory is more than a physical theory. It is a philosophical shift, a new way of thinking about the fabric of nature. It blurs the line between mathematics and physics, between structure and substance. It suggests that what we perceive as matter and energy may be manifestations of deeper geometric vibrations. It challenges us to think beyond observation, not in opposition to experiment, but in anticipation of the next leap forward in technology or thought. Its strengths are undeniable: a natural inclusion of gravity, an escape from the infinities that plague quantum gravity, a framework rich enough to produce the Standard Model, and connections to deep mathematical truths that seem too elegant to be coincidental. Even its speculative elements, like the landscape and multiverse, force us to confront the limits of what science can explain and what it means to make predictions in a vast cosmos. Critics point out its lack of experimental verification, the ambiguity of its many solutions, and the risk of becoming disconnected from empirical science. These are valid concerns, and they underscore the importance of rigorous dialogue between theory, observation, and philosophy. But perhaps the true legacy of string theory lies in what it has already achieved. It has expanded the imagination of physics. It has taught us that unification might not be simple, that the universe may be far richer and more complex than any one set of equations can capture, that beauty, symmetry, and consistency can be guiding principles, even when the path is long and the destination uncertain. In the bigger picture, string theory is not a final answer. It is a bridge from the known to the unknown, from the classical to the quantum, from space to information. Whether it proves to be the ultimate theory or simply a step toward something deeper, it has already shaped the intellectual terrain for generations of physicists, mathematicians, and thinkers. And so, the strings continue to vibrate, not just in the equations of theorists, but in the very fabric of our curiosity. They whisper that the universe may be woven from something more subtle than particles or fields, woven, perhaps, from the music of the cosmos itself.